Okay, it's 9:45. Let's get started. Good morning. How was your evening? Had fun? Did you go? Anybody do any sightseeing in Bhubaneswar? No? No. Okay. Were you guys able to finish that spreadsheet? Mostly? Okay. We'll go over that in the tutorial. So, I did receive several of those homework zero submissions, uh, but I will keep track before lunch. Submitted no lunch for you, right? We agreed to that one. So today we're going to have a lot of stuff, mostly on subgrade evaluation, and we're going to focus on a lot of tests that you have heard of. uh, I think you have heard of all of them pretty much. I don't know how much details you have gone into, so we'll cover a lot of those stuff. Talk about CBR, plate loading, a little bit of VM stabilometer, quite a bit of triaxial. Then we'll take a look at some other stuff as well. Falling weight deflectometer. We'll see how much we get through, because it's a lot of stuff. We should be able to also talk about back calculation after today's session. I don't think we'll have time to go over the full back calculation software. We may do that in the tutorial maybe tomorrow, because today is something related to triaxial. We'll figure it out. And then we're going to talk about some DCPs, some expedited field tests and stuff like that. Okay, this is the Menti link for today. So scan this, keep it open, or keep it in your browsers. We'll get to that. I haven't launched anything yet, but you're going to use that. Okay. Again, I as I said yesterday, this slide set is borrowed from a lot of people. Some of my contribution, of other people's stuff that I have learned over the years. My PhD advisor, L03 Subgrade, he's a very well-known expert on transportation geotechniques, so I borrowed a lot of stuff from him, so acknowledgements. We're going to talk about strength. We're going to talk about why strength is important, what properties or what behavior of a pavement is affected by strength. We're going to talk about plate loading, triaxial, then we'll go into stiffness, and we'll talk about modulus, not really go into resilient modulus a lot, but we'll go into modulus from plate loading. So that's a very common thing that people do. We are going to talk about what are the advantages, what are the disadvantages for doing that. Then we are going to talk about some stress strain curves and stuff like that. What are the properties that are of interest to us? We want to know strength, stiffness, then permanent deformation, which is basically your plastic deformation, which manifests itself as rutting, right? So we're going to talk about what affects rutting, how do you measure it, how do you quantify it, and day 3 and day 4 is going to be a lot more of repeat loading and stuff like that. Swell potential, frost action we'll just briefly mention, and then moisture sensitivity to strength and modulus, we'll go over that quite a bit, how moisture affects these things and stuff. Okay, before we go, I want to do a very small exercise on compaction, and this is something that you all said relatively comfortable doing this, right? So how many of you have done lab compaction tests on soils, aggregates, anything? Okay, what's the test called? Proctor test. And what, there are two variations, right? Standard and modified. Who remember the ASTM numbers? You remember IS numbers? Okay, fair enough. So it's from what I have gathered is that IS is basically based on ASTM directly. So I don't remember the IS numbers because I don't work with those, but it's ASTM 698, D698 and D1557, okay? Those are the two numbers. So I have a little exercise for you. here is the screenshot of the two titles. Okay, read the first title. Somebody, I forgot your name, I'm sorry. Yeah, read the first one. 600 kilonewton per kilonewton meter per meter cube, right? What's missing? What's missing from this title? Proctor, right? What's the second one? Who's going to read the second one? Akshay, you want to read the second one? $2,700 kilonewton meter per meter cube, right? Again, what is missing? Proctor. So here is news for you guys. The test methods that you follow are not Proctor methods. Okay, let me show you why. This is the trivia I do all the time, and that is the reason I do it is because this was first time highlighted to me during my PhD dissertation exam by Professor Marshall. Oh, by the way, did you guys read the paper yesterday? Marshall Thompson's paper? Okay, good. So, no, this is a modified one. You can't do that. I need the standard. Okay. The equipment and procedures are similar as those proposed by R.R. Proctor with this one major exception. His rammer blows were applied as 12-inch firm strokes instead of free fall, producing variable compactive effort depending on the operator, but probably in the range of this, and standard effort test is sometimes referred to as the Proctor test. So what I'm trying to say is when you do an engineering document, do not write it is a standard Proctor test, because you are not doing a standard Proctor test. Nobody is doing it, right? So Proctor, when he developed the test, he developed it for sandy soils, and it was firm blows. So what means is that you take the hammer, you actually bring it down, and you use your hand to do this. It was not a free fall. It is not just mgh as the energy. So there is a lot of variation in that. So it was actually modified into that. So that is the reason the tests should now be referred to as standard compactive effort or modified compactive effort. Do not say standard Proctor, modified Proctor. Colloquially, it's okay, like when you talk about with people, but in engineering reports, it's actually wrong. I mean, 90% of the people don't realize it, but that's how it is. So just a little trivia before we get started. All right. So we're now talking about pavement design, right? Or pavement, how are you going to do a pavement design, and you need to classify or quantify or characterize your subgrade. So this is a NCHRP 382 that was done by Professor Anand Puppala pretty long back now, and synthesis reports, if anybody has read them, they are actually survey of state practices. It's not a research report, it's a practice report, it's a synthesis of practice, right? People said that, you know, procedure used for pavement design, some people were still using 1972 AASHTO. A lot of people are 1993 AASHTO. MEPDG was only one agency. Agency specific mechanistic procedures, and then no response and stuff like that. So what I'm trying to say, the numbers have probably changed. I mean, this exact survey probably has not been done over the last 10-15 years or something, so I don't know the exact results. If somebody did it, you can pull it up. But the idea is that a lot of people are still relying on the AASHTO 1993 or a version of it and stuff like that. Of course, the MEPDG number is now larger, but it's not as widespread as one would imagine. I mean, people would think that, oh, MEPDG, if the project finished in 2006 or something like that, 2006 or something. It's been about 15-16 years or more than that, that then the MEPDG was developed. But implementation has still been challenging. A lot of people are still playing with it, but full-time implementation has not happened. Then there are other agencies. Corps of Engineers, they actually do, for flexible, they just do like a CBR based method, right? One of the main challenges of the Department of Defense is that when they are going to like a new military base or something, when they are establishing, they don't have 6 months to collect soil sample, wait for the results, do a detailed characterization. They need the information like yesterday, right? So that is the reason a lot of their work has to still be based on empirical or quick tests or something. They cannot do even a simple CBR test is a 96-hour soaking, right? It's a 4-day. That's a lot of time. You can't afford that, right? So a lot of quick tests and stuff, people do modulus of subgrade reaction. FAA or Federal Aviation Administration, they also did modulus of subgrade reaction, and then they actually have this LEDFA or far field. Now it's called far field now. I think that's the new one, current name, which is the analysis software and stuff. And ASTO, of course, the ME design or MEPDG, will talk a little bit about that. So CBR, people were using 19 states. R value, how many of you have heard of R value before? No? Okay. How many of you have heard of the Weem stabilometer or stuff, something like that? Or do we cover Weem method of mixed design here in India? No, no. Only Marshall and Superpave and stuff. Okay. Okay. So we'll talk about it. The R value is a resistance value. Triaxial testing will go quite details, and we'll take a look at those. So 19 respondents use resilient modulus obtained from different methods other than laboratory and field measurement for subgrade and unbound basis respectively. What does that mean? So if you do an ASTO, I know some of you don't have any pavement design background, so that's a little challenging to understand everything. But if you look at it, even if you go through your ASTO 1993, subgrade modulus is an input, right? That is how it all starts. That's the support that you go to start and stuff. But how do you get the modulus? Where are you getting that from, right? A lot of times you will hear a thing like 1500 CBR or something like that, or I think there is a 2555 CBR raised to the power 0.63 or something like that. There is another equation or something. But the whole idea is we are using something to predict something else, and what is the logic behind it, what is the accuracy behind it, how much error are we introducing, what is the tolerance level and stuff like that, right? So we need to be careful about. How to characterize structural support? Again, some people followed 1993 ASTO, some people followed local correlation. Most of them, a higher number, actually did local correlations. Now, as I said yesterday, empirical methods, as long as they are applied in their own domain, may actually work. Now, whether you are doing it the right way or not, that's a different question. We'll get into that. So that's basically what it is. So now we're going to, so that's just the basics. Now we are going to go one step at a time into each test method, and we'll talk about it. Okay. How many of you have run CBR? Quite a large number. Good. Soaked or unsoaked? Soaked. 96 hours. Has anybody done unsoaked stuff? Okay, some of you. Okay. So we'll go into that. So those of you who have not, CBR is basically the oldest living dinosaur in the world of pavement engineering. Okay. It's a California bearing ratio test. California is because it came out of California. The person Porter, Jim Porter, I think is his name. He developed this. He was working for the California Highway Division, and then he basically said, found a magical aggregate. Okay. When I said magical, it's not, at that time it was perfectly fine. He found a well performing aggregate, and he said, this is my reference, right? What we are going to do is I'm going to run a test with a plunger. It's a metal plunger that is actually going into the soil or into the aggregate at a given, and I'm going to keep measuring the resistance that the plunger is experiencing, and I will pick it at two different values, 0.1 inch, which is 2.5 millimeter, and 0.2 inch, which is 5 millimeter, and at those values I'm going to measure the pressure, and I'm going to compare that with the pressure I experienced when I tested my magical aggregate, right? And that ratio is what is California bearing ratio is, right? The thing is, so this is a company called Gilson. They sell a lot of equipment. This is their website. I just got it, and then if you see, there is some CBR ranges that they report and stuff. This is like a schematic of the thing. Of course, there is no proving ring these days. You have load cells, right? You don't need a proving ring. You don't need a dial gauge. You have an LVDT. You just go and you measure and stuff. This is the specification 1883, 3 square inches of area, which is 1.96 inches of diameter. You can convert that into millimeters, and then you have a 6-inch mold or a 4-inch mold or whatever, right? 6. So what you do is you have the crushed stone values. So at 0.1 penetration, the crushed stone had a 1000 psi resistance. At 0.2 penetration, it had a 1500 resistance. So that's the crushed stone. That is the magical aggregate I'm talking about. And then you test your own aggregate or soil, and then you take the ratio, like whatever your value is here, 125, you divide that by 1000. So your CBR is 12.5. Right? There are two schools of thought. Some people say that it should always be referred to as a percentage. Some people don't refer to as a percentage. I'll let you do what you do, right? I usually write it as a percentage, but it's not a requirement. The mathematics is that you actually measure at both of them. If by any chance your 0.2 millimeter measurement is higher, then you actually report that. You don't go with the 0.1, right? So that's basically this. Use 2 greater than 1. So you do a 4-day soak, 3 square inches, and then it record, and then you compare the soil strength. Okay. So typical results, if you look at it, this is because CBR is so old. These graphs, some of these graphs you are going to see are going to be very old. This is like the crushed rock, the reference that they had, and this is penetration, and you actually try to get typical values for something. Some of the things I'm not very familiar with the Indian practice, but the point is usually for a crushed rock you should get something at least 80 or something like that. That's a good number. A lot of times you get 100 or something, or even greater than 100. We'll get into those things. So what limitations somebody already did it? Was that launched already? Okay. All right. Associated with the CBR field, with the CBR test, it's not necessarily field. I'm talking about lab. I'm talking about CBR. Okay. So the person who has already done it, you can do it again. I have allowed multiple responses. So question is, what do you think are the limitations of CBR before I go into anything? Yes. Yeah, we'll get to that. We'll get to that. Okay, we have some good responses. Uh, let us go through some of them. If you have input, folks, please continue doing this. I'm starting to talk because I see we have so much material today. It's already 10:15, and at 11:15 we're supposed to have a break. In 1 hour, I don't know how much I can go. So we'll keep moving. I see some of them are practical concerns you all have, like for example, human error. Uh, Test takes a lot of time. Uh, it's difficult to run on clay soil and stuff like that. True. Okay, but I actually have a different question. So you have a steel plunger that is going into the soil, right? When was the last time you saw a steel plunger going into an actual pavement? No. It's a bearing capacity kind of a test, like a bearing. It's California bearing ratio. Everybody has taken geotech classes, I'm assuming foundation classes and stuff like that. So capacity is stuff like that. Do we design pavements for bearing capacity failure? No, we don't, right? Another thing, what's the diameter of the plunger? I said 1.96 inches, whatever that is, whatever that is, right? 50 millimeter probably, right? And what's the diameter of the mold? 150, right? So, and what's the depth? Do you remember? 127.3. That's 5 inches. No, isn't it closer to 4 inches? I think it's 101 or something, right? Closer to 100 maybe. I think. I don't remember. I haven't run this for a long time. Do you remember the concept of a slip surface? Like when you do a plunger or a bearing capacity, there has to be a slip surface that develops, right? You're inside a steel mold. What is the likelihood that actually a slip surface is developing? It's not. Your mold is severely affecting the development of a slip surface, right? How is your pavement loaded? How is your pavement loaded? When you it's my fault. My Mac is not on charge. I'll put it to charge. What kind of loading do you experience in a pavement? Who said cyclic? You're going to buy me lunch today. No cyclic. What did we say yesterday? Repeated, not cyclic, right? We don't load pavements in cyclic. Okay, so we have repeated loading of a tire, right? Of some kind of a rubber thing or whatever, right? Whereas you are trying to simulate that by taking a steel plunger and pushing it into a soil, right? And you are saying that we are going to get modulus out of this because the mechanism is completely different. The loading phenomenon is completely different, right? So CBR is a good index test, and it is a good test when it was developed. When was that? 1930, 100 years ago, right? Here is the fun part. 1977 keynote address by Stephen Brown, okay, 50 years ago at Nottingham. He said Jim Porter, who as the soils engineer for the state of California introduced this, said in 1938 the bearing values are not a direct measure of supporting value of materials. In 1950 he said the results are influenced only to a minor degree by elastic deformation. Okay. In 1950 Turnbull said the CBR is an index of shearing strength, and we use it all the time to predict modulus, right? So the person who developed CBR said don't do it, but after World War II it was widely accepted, and that is the reason we are keeping doing it. Okay. Oh, by the way, I think Dr. Sahu probably said this already. At the end of the class, maybe on Friday or something, mostly we will give you all PDFs of all lectures and stuff. So it'll stay with you. So you'll have PDFs. So the point is a CBR, and then in Crony 1977, the shear strength of a soil is not a direct interest to the road engineer. The soil should operate at stress levels within the elastic range. Pavement engineer is therefore more concerned with elastic modulus of the soil and the behavior under repeated loading, not under monotonic punching kind of loading, right? That's not how you're going to predict modulus. But it does have, it is an index test. It does give you some stuff. Okay, it's not a fundamental property. It is not based on physics. Like you cannot do an equation for it. You cannot use a CBR directly to in a constitutive relationship or something. Right? It's not a fundamental property. Soaking. Who asked? You asked, right? No, you asked. What's your name? Ashish asked, what is the point of 96-hour soaking? Why do we do it? Who can answer that? Why do we soak it for 96 hours? Say it again. Saturation. Yes, yes. So water is the worst thing that can happen to your soil or aggregate, right? So you're basically soaking it to simulate, of course, 100% saturated and simulate the worst possible moisture condition that you are going to, that soil can have, and you are going to get a very, very, very conservative number. But the problem with the CBR by that method, and that is the reason I didn't answer your question at that point, is because we were going into this. In the field, how many times do you actually see the layer is completely flooded? It's not. I mean, sometimes it is, but then the water gets removed. How many times do you see the entire layer is at one moisture content which is 100% saturation? Never happens, right? So not uniform moisture condition in the field. It's not a realistic situation. Something wrong? Okay. Static punching assumes good CBR indicates good performance under repeated loading. Again, strength versus modulus, very different things, right? And if you want a reminder on that, how does that work? You have a stress versus strain curve, right? Epsilon sigma. This is your strength. This is your modulus, right? I can have a much lower modulus but a much higher strength. I can do. You can have it, right? So the question is, this and this are not always the same thing. You should not be using it, right? So that's the limitation. Mold size, I told you already. Bearing capacity, you need the depth of 2 to 3 times phi just to develop a proper bearing capacity. If you go back to your Terzaghis bearing capacity failure and stuff like that, right? So that's the reason mold size affects it. Also, there is this is just a very trivial detail. I'm assuming whoever is running CBR, you have modern equipment that actually does the zero correction at the very beginning, because there is some seating that happens. It's just a little trivial thing. I'm not going to spend much time. It is very common practice to measure when you do a CBR test. You do it at multiple moisture contents, and then you actually report it just like you report a moisture density curve. Like you have a moisture density curve like that, and you actually correspondingly you report the CBR values here and stuff. And this is I think you probably also do swell testing on CBR as well, right? I have been primarily an aggregates person, so I have only like once or twice in my life. So I don't know a lot about swelling, swell tests and stuff. But the point is soaking. So this is one more thing I wanted to highlight to you, is a lot of agencies, when they realized the the disadvantage of 100%, like 96 hour of soaking and stuff like that, they actually move to what is known as unsoaked CBR. They prepare it, they test it at that moisture content, the molded moisture content. And as you can see, as the moisture is drier, the CBR is much higher. It doesn't follow the bell-shaped curve. Like if you see a typical CBR test should follow a typical moisture density kind of a shape. It's a bell. Whereas the value actually peaks a little bit on the left side of the OMC, because dry is better. We're talking shear strength, right? Drier is better, so it will peak on the left always. But the point is, for all practical purposes, this line is of a lot more interest to you, because in practice you do, unsoaked CBR. I actually don't know of many agencies in the US who do actually soaked CBR. Unsoaked is a lot faster, and it gives you some value and stuff. So this is just another test result. This is a typical way of presenting. You do a density and the CBR on the second plot and stuff. And as I said, the CBR peaks on the left side of the OMC for a compaction and stuff. Typical results: when fines increase, CBR decreases, because it's a strength. Like if anything, it is a strength index, right? It gives you some kind of shear strength. I would be much more comfortable if you used CBR to predict shear strength than CBR to predict resilient modulus. It's a strength index for all practical purposes, right? What does CBR greater than 100 mean? Right? It's an arbitrary reference material that you chose, which is probably not available anymore, right? So what is greater than that mean? Like how do you compare that with respect to your mechanistic performance and stuff like that? It's still questionable, right? Compaction affects a lot. This ASTM D1557 is your modified, this is your standard. And again, in this short course, we are not going detailed into compaction, because we kind of assume that you have a good background. You know that compaction is MDD and OMC, these are not fundamental properties, right? They are dependent on the compactive effort. So a lot of times you change the compactive effort just to study. Like in this study, this was another study by, I think, Professor Thompson. What he did is he developed an intermediate compaction. Like if modified is, say, 5 layers, if standard is 3 layers, he just made a 4-layer sample. So that's intermediate compact, like somewhere in the middle and stuff. And as you can see, as moisture content increases, because it's a clay soil, CBR collapses really, really fast. So moisture is a really bad thing. That is the reason you soak, is because you are going to get the worst possible thing. But what is the point of soaking an aggregate if it is a very low fines aggregate? Because what happens to the water? It just drains, right? So your water does not really change the behavior as much unless you have plastic fines and stuff. So that's basically. Soil groups, some people have A1, A2. I mean, they learn AASHTO classification as well, right? Most of them, yes. So this is AASHTO classification, not USCS, right? Unified Soil Classification System, AASHTO is the other one that was used in America. A1, A2, A3 is the granular, A5, A6, A7, these are the fine grained soils and stuff. But bottom line is, so IBR actually is what Illinois came up with, is the Illinois bearing ratio, and then they just had ranges and stuff. But the bottom line to talk about is, for any soil classification, you have huge ranges. So if you just say that I have a CL, tell me what the CBR is, it's not possible. It has a lot of things that affect it, right? So it's not a fundamental property, so we should not be focusing on that primarily. Granular soils, if it is not much fines, then CBR is basically a function of density. The more you compact, the better they pack. On the other hand, I told you something yesterday is the challenges with open graded aggregates. And I gave the example of glass marbles, right? No matter how much you compact, they are only going to get somewhere. And then if you do a CBR, it will look like really good crushed aggregate, but you will get CBR values of like 10, 15, because it's not stable. The matrix is not stable, right? So those are all. Does that mean the material is bad? No. You confine that material, it will take a jet plane. It will withstand a jet plane. So that's where we're going to get into the stress dependent behavior on day 4 and stuff, when we talk about why aggregates are great value when you actually confine them properly and stuff. Then you can load it as much as possible. Fines matrix, you can have no fines, just the right amount of fines, and greater amount of fines than optimum and stuff, right? Moisture content, certain point, if there is no fine, the water you add, what happens to it? It escapes. So your material or your sample does not really change behavior because the water is gone, right? So it's very important to realize where you have optimum fines or greater than optimum fines. Of course, optimum fines, because the matrix is so stable, you have really good resistance and stuff. So that's what the example, again, if you go back to the railroad ballast example, the fouled versus unfouled, that's what I was talking about, right? If it's fouled ballast, if it is dry, it can actually be really good sometimes. The problem is when it rains, it collapses, right? You have a lot of correlations like this. You can have AASHTO correlations, ASTM, the USCS, basically the Federal Aviation Administration, the R value, modulus of subgrade reaction, bearing value and stuff. So CBR, you can actually have some ranges and stuff. But look at, let's take something like an ML, like look at the range of the ML here. So the CBR can go anywhere between 4 to 15 or something like that. So it's over, like, if you go into an A24, A25 soil, it's a 20 all the way to probably 80 and 90 and stuff. So it's a huge variation. So it's not a fundamental property. It is not something that we should bet our money on and stuff. So it's just background. That was a quick overview of CBR, right? What are the challenges? Why you should? It's okay to test, but you need to take it with a grain of salt. You need to remember what's going on. What are you testing? What is it telling you? It's not something that So that is the reason. That is the reason the 1500 CBR is something you can say that I have tested. So let's say there is an agency who is dealing with the district of Khordha or something, and they encounter 4 or 5 different types of soils, and over the years they have tested the soils, they have characterized it, and they have developed a database or something saying that, okay, my CBR relationship is something about resilient modulus at some kind of a stress state is about 2500 times CBR or something. That's okay, because they have done it for their soil. They know what is representative. We cannot use it widely. It's just not something you should be doing. Alternatives. The first one we're going to talk about is Weem stabilometer. Okay. So Weem stabilometer, if you ask me, it's actually not. So there is a gentleman called Weem. I think his name is HC Weem or RC Weem or something. I don't remember his exact name. He was again another engineer working in California. He came up with this mixed design methods for asphalt and stuff. So there is Marshall, there is actually Weem, and then there is Superpave, and now BMD and stuff like that, right? Weem actually developed something called a stabilometer, and I am actually a bigger fan of the Weem stabilometer than of CBR, because to me it's a lot more scientific than just punching a soil or something. The whole idea is it's related to Poisson's effect. What is Poisson's effect? Say again? That's Poisson's ratio. minus epsilon 3 over epsilon 1. That's Poisson's ratio. What's Poisson's effect? Yeah, exactly, something like that, right? I mean, I would not say x and y because I can always put x and y in the same direction, same plane. But yes, longitudinal axial compression will lead to radial expansion and stuff like that, right? So Wehm stabilometer, what it does, it is basically measures the resistance to displacement is expressed as a function of the ratio of the transmitted lateral pressure to that of the applied vertical pressure. So when you apply a certain amount of vertical pressure, how much lateral pressure is being transmitted? When you have a balloon, when you squeeze it in one direction, it is going to expand in the other direction, right? Called Poisson's effect. So the stabilometer is actually based on Poisson's effect. So there is a little video here. We're going to play this.
Okay, you'll take the adjustable base out of the oven, place the stabilometer onto it. You're going to take a measurement from the bottom of that metal ring down to the top of the base. It should measure 3.5 inches.
This is also used for asphalt, by the way. So you'll see this one is actually for asphalt, but it's the same thing.
The oven temperature is always 60 C or 140 F. Okay, once you've taken that measurement, you're going to be taking the thick-walled cylinder out of the oven, called the follower, placing it into the stabilometer, and then you'll be turning the horizontal pressure up to 20 psi, and then you will allow it to stabilize. While it's stabilizing, it's heating the oil in the bladder. Once it has stopped moving, you're going to take the follower out, place it back in the oven, and get the thin-walled cylinder out, the calibration cylinder, place it into the stabilometer, turn the horizontal pressure to 100 psi, and once again allow it to stabilize. Simultaneously, you'll be adjusting the turns displacement dial to 0. So it takes a little time for it to all stabilize. When you're done, you want the horizontal pressure at 100 and the turns displacement dial at 0. Once you have both of those dials set, you're going to be turning the horizontal pressure handle out exactly 2 turns, watching the turns displacement dial.
So this is all related to calibration. You should not worry about that much. The initial part.
So if the needle is a little above the 5 psi, you're going to have to let air out. If it's below, you're going to have to let a little air in. So with the calibration cylinder still in place, with it set at 5 psi, you'll measure the exposed piston length, which needs to be 2.8 plus or minus 0.2, which tells you if there's enough oil in the bladder. So you'll be taking the calibration cylinder out then, and you'll be removing a specimen from the 140 oven, placing powder around the outside of your specimen, or you can actually put powder on the inside of the stabilometer bladder. Allow it to slide down into the stabilometer. If it doesn't slide down, turn the handle out till it easily slides down. Making sure it's in there firmly, and you're going to place a follower above it. Turn horizontal pressure to 5 psi. You're going to carry the stabilometer over to United compression machine. The proctor will lower the head after you've centered it underneath there. They're going to lower the head until it's just about touching the follower. Once they've completed that, then you're gonna have to recheck and make sure that your horizontal pressure is still set at 5 PSI. Once you've done that, then the proctor will start the test for you. They'll ask you what the rate is, which is 0.05 inches per minute. They'll ask you when you're gonna take your first reading, which is at 5,000 pounds. You'll be able to watch on the computer screen when it gets close. You'll take your reading, which in this case is about 32, write your reading down.
So this is all I wanted to show you. Oh, it switched. That's okay. This is all I wanted to show you. What did he do? They actually applied load from the top using the compression machine, and then they saw an increase in the pressure on the lateral reading. It was 5 or something, it went to 30 or something, right? Why did that happen is because of Poisson's effect, right? You squeezing, it's expanding laterally, there's the bladder is full of oil, and that is the reason it is experiencing, right? So if you want to calculate the R value, this is the equation, okay? And what do you see here? Take a look at it. So think about it this way, folks. D2 is the displacement of the stabilometer corresponding from increasing horizontal pressure from 5 to 100 psi, right? So if it's a completely rigid material, to increase the pressure from 5 to 100, how much will be the displacement? Theoretically, full rigid. So what's the displacement? 0. So D2 is 0. So go to that equation. D2 is in the denominator, so that becomes 0. So that term basically becomes infinity, right? I mean, don't go into calculus into me, but yeah, that's infinity, right? So 100 divided by infinity becomes 0. So 100 minus 0 becomes 100. So R value is 100 when it is 100% rigid, right? On the other hand, if it is water, what is going to happen? When you increase V, pressure in the vertical direction, how much will be the increase in horizontal direction? Same pressure, hydrostatic, right? So PV over PH becomes 1. 1 minus 1 becomes 0 plus 1 becomes 1. 100 divided by 1 becomes 100. 100 minus 100 becomes 0. So water is 0. So these are the two extremes. And then you are somewhere in the middle when you are testing your soil. Right? So that is the reason, because I find it much more scientific than just plunging a CBR and trying to compare it with an aggregate or something. Right? So, but again, it's still an index test. It is not, it doesn't give you constitutive values or something, but at least the index is based on Poisson's effects and stuff like that, which is what I like, right? So that's what R value is. That is something that used to be tested in the past. So Idaho, where I was before I moved to Oklahoma, they still used R because they're near the west coast and stuff. California, they still have a huge database of R values. The state of Washington, where Seattle is, they have an R value database and stuff like that. Some of them are slowly moving away, like Idaho is moving away from it, but they still have, the older engineers will be able to really tell you that, oh, this is an R value of this is an R value of this, and stuff like that. Okay, so we covered 2, CBR, stabilometer. Now go to plate load test. Honestly, you all probably have seen more plate load testing than I have, because India, I know that there is a lot of plate load testing that happens, right? In US also it happens, or in airfields and stuff, in army installations or military. I haven't seen as many in my life. I've seen, I think, only 5 or so. So it's a static loading test. It assumes what is known as dense liquid foundation or Winkler foundation. Does anybody know the definition of a Winkler foundation? Question? Yes, yes, but what is the main property of those springs? Yes, one keyword. Well, no, that's not the, that's under a slab, that's different. That's not Winkler foundation though. You are on the right track. You're just missing one keyword. The deformation at any point depends on the load at that point only. There is no shear transfer of the deformation happening. Like, so what I'm trying to say is there is a spring here, there is a spring here. If this spring deforms, does not mean this one will deform. It's only dependent on one point. That's basically what it is, right? This is we talked about this yesterday. So it's pressure is equal to K multiplied by deflection. So the unit is PSI per inch or PCI, pounds per cubic inch, or something like that, right? Or Newton per millimeter cube or something, right? It's conducted to measure subgrade soil input parameter for concrete pavement and slab thickness design. This is another little video that actually will show you. This is by Tensar, actually gives a good input for that.
Hello, and welcome to this first episode of Tensar Ground Coffee. A few minutes on ground engineering to enjoy while having your coffee. So in each episode, we're going to cover a snippet of ground engineering that is usually somehow related to Tensar applications. Now, just recently, we've been doing quite a few tests on
Volume
platforms for piling rigs constructed out of our mechanically stabilized.
Let me see if I can change the audio source to the room because I'm connected to HDMI. I don't know if that's possible. Is there a speaker in this room? I connected it to the other one. I don't know where the volume is. Huh? It should. It's not. No. No, yeah, no. That's it. Sub maximum. No, the volume previously the volume was coming through my laptop right here. This was
on working platforms
here.
for piling rigs constructed out of a
No, it's still here. Not the room.
Hello, welcome to this first episode of Tensar Ground Coffee. A few minutes on ground engineering to enjoy while having your coffee. So in each episode, we're going to cover a snippet of ground engineering that is usually somehow related to Tensar applications. Now, just recently, we've been doing quite a few tests on working platforms for piling rigs constructed out of our mechanically stabilized layer. We've been using the plate load test, but we've been using big plates. So why is it important to use a big plate when performing a plate load test on a working platform? Well, let's find out why. Brian, over to the flip chart, and I'll try to explain. So you have a ground level like that, a ground surface, and you have a plate load test. You all know what a plate load test, a circular plate that you put on the surface, you load it, and you measure the settlement. It can tell you the stiffness and the bearing capacity of this ground if you load it high enough. So the plates start off at about 0.3 meters or 1 foot diameter, but you can get bigger plates. Another common one, 0.6 meter diameter or 2 foot. Now, what difference does it make the size of the plate? Well, the depth of influence or the bulb of pressure is directly related to the diameter of the plate. So the depth here is up to about 2 times the plate diameter. So if you have a bigger plate, the depth of influence is going to be much greater. So even if this was all the same soil, you would still get a different result from this plate compared to this plate because you are testing a different volume of soil. And maybe the properties of the ground get different as you go deeper down. Now that becomes even more important with a working platform. Now you've got 2 layers. You've got the stronger working platform layer of compacted granular material. That's the working platform. And then underneath that, you have the softer subgrade. So now the bigger plate is influenced by this softer, weaker material. So we'll definitely get a softer, weaker response with this plate compared to this plate, which is only affected by the higher quality working platform material. That is important for working platforms because imagine we have a piling rig, for example, that is going to use this working platform, and that has a track width, say, 0.7 meters. What will be the depth of influence of that track? It will be similar to this large plate here. So clearly, to verify the design of this working platform and that it is safe to support the piling rig, you need to do a test with a plate that has a size, a diameter that is as close as possible to the track width so that the depth of influence is the same. So that if you loaded this to bearing capacity and verified the bearing capacity, you know you have sufficient bearing capacity for that plant there. That small plate is clearly inadequate to verify the design of the working platform because it does not have the correct depth of influence. This could be used as a quality control test just to check whether the granular layer is as was assumed in the design and has been compacted according to the specifications. But for verifying the design and the safety of the working platform, clearly you need to have a plate size as close as possible.
I think that's we can skip the remainder of that. But that was the bottom line I wanted to make, is that you should be using a plate load test of the right diameter so that you know what you're trying to study, right? Standard is 300 millimeter. Is it 1 foot? Yeah, 1 foot diameter is 300 millimeter, 30 centimeter. 30 centimeter diameter is the standard one. And then for airfield pavements, you have different criteria. There you can go to 30 inches over there. It's too expensive. It's very, very time taking because you need to mobilize like a truck to have because it's your so you have to have like a reaction frame basically. You have to it takes quite a lot of time. It's not very quick, but when you are trying to do airfield pavements and stuff like this is an example. When I was a grad student, the Chicago O'Hare Airport was undergoing the modernization program back in 2004 and stuff, and they were doing these kind of testing. Those of you who are familiar with plate loading testing, what's the purpose of the stacking of the plates? Any idea? Say it again. Towards stress concentration, but it's a plate. Why can't you just use one plate? Say it again. It's related. You are actually trying to avoid bending of the plates because we are trying to measure the deflections at the circumference, right? So the plate actually sometimes bends as well. So if you make it thicker, the bending stiffness actually increases and stuff. So it's actually to avoid errors and stuff. So how do you measure? There are different types of measurements. I don't know about the Indian standard, but the Army Corps of Engineers, they actually measure at 10 psi divided by the corresponding deflection at 10 psi. Okay, whereas the Portland Cement Association for concrete pavement design, I'll show it in a second, what they do is they do the pressure divided by a given deformation of 0.05 inches. So there are two ways to measure, right? One is fix the stress, target stress, then measure the corresponding deflection. Here they are fixing the deflection and measuring at the target at the corresponding stress stuff. Which one it is, it doesn't really matter. You just need to know what you are trying to do. There are some corrections. This is a correction for bending of the plate that I like to show. So think about it this way. If you have seen a plate load test, you're measuring the deflection on the circumference, right? So if the plate bends, will you record a greater deflection or a lower deflection? Lower deflection, right? So your K will be artificially higher. So you have to do a correction where you are going from say 350 to something like 300. Where did this curve come from? Empirical, right? This is all based on experience. This is all based on data and stuff. But that's the kind of correction they do. They have another correction for saturation. We're not going to spend a lot of time on it because you're not going to use it as much. If you're doing a concrete pavement design for sub bases and stuff like cement treated sub base, you have K correction. You have granular sub base thickness, you have a K correction and stuff. So it's all taken care of when you're trying to say that what is your zone of influence and what is it affecting and stuff. Again, as I said, a lot of stuff we need to cover, so I'm going to move on. Limitations: not easy to conduct, time consuming, needs a large reaction frame. Again, not a fundamental property. It is dependent on a lot of other things: plate diameter, saturation, and you have to really know that there is no plate bending happening and stuff. And okay, and one more thing I wanted to highlight here is another very common approach is relating resilient modulus to modulus of subgrade reaction. There is a factor of 19.4 actually they use. Okay, there is a reason why I actually had slides but I deleted it because we don't have time for all of that. Let me ask you this: when you are measuring modulus of subgrade reaction, like when you're measuring K, are you measuring elastic or plastic? Is it plastic? Is it 100% plastic? Or do you actually know how much is it elastic and how much is plastic? You don't know. It's a combination of both. There is plastic for sure, there is no doubt about it, but there is actually some elastic happening as well, right? But resilient modulus, when we go into that, and I'm assuming you know this already, is it's 100% elastic. You're talking about elastic behavior, right? So you are running a test where you are measuring even plastic deformation, and you are using that to predict only elastic properties, which is resilient modulus, right? So that's the challenge. That's the main lacking of that. There is another thing called automated plate load test, which is these days getting very popular. It's actually a field rig that was designed, and they actually do a repeated plate load testing to do what is known as in place resilient modulus measurements for layers and stuff. It's a very modern approach, modern thing. I just wanted to give you a glimpse of that and then pretty much stay there. I mean, I'm not going to go into that, but it's a way to measure resilient modulus of layers in the field. It's a lot of state DOTs like Minnesota, Iowa, and stuff. They're utilizing this quite a bit. This David White, he was a professor at Iowa State before he became a private consultant, and Pavana Venapusa, he's actually from India. He's a Telugu guy. He was his PhD student and then postdoc, and then he's their lead technical person and stuff. So that's plate load test for you. Just an overview. You get modulus of subgrade reaction. You try to link it with resilient modulus. There are disadvantages, but it still uses practice and stuff. So we finished CBR, we finished beam or stabilometer, and now we finished plate load test. Now we go into triaxial. Okay, we'll go for 15 more minutes. We'll take a break and then come back again. This is going to take us some time. Okay, triaxial testing, and this is where spend some time because when I